to Jeff's TK, advanced TK tutorial?
Yes.
If you go to TK Live, there is a drop-in script that you could throw into your TK 8.3 application that will make it look nicer.
Oh, really?
So you can just drop it in there.
Okay.
So you don't have to go to immediately, but it's a pretty good reason to go TTK at 8.5.
All right, thanks.
In your examples, you showed where the H was regular and not deformed.
Yeah.
Can you handle where the H is deformed such that the top of the H is not as large as the
Yeah,
bottom?
it can. But that's just an example because the multiple connector edge could be everywhere, could be anywhere. Yes. That's it.
Thank you very much.
Thank you.
We seem to have
We have John. Andreas is next.
and
Yes, he's not there.
very good. So
Yes.
so Andreas is next, and well,
Yeah.
I think he needs no introduction, or if he does, I'm not the one to give it.
This is the internals section, and Andreas will be talking mostly about reflected and transform channel.
I didn't consider season in my title. Okay, anybody listening? No, we will. Good. Then I will certainly talk. I am Andreas Kubis. I work for Active State under Jeff, and my talk is about reflected and transformed channels, which is basically the writing of channel drivers and channel transformations in Tcl. And as such, it doesn't really provide something new. However, it makes access to this complex system, channel drivers, channel transformations, easier, and as such should make it also easy to prototype something, experiment with drivers, or write on-off drivers. Okay. Yeah, for the rest of the talk, I will skip the history section and the implementation section. And I will give first some examples to get your imagination running, what you can do with channel drivers. And maybe you have then your own ideas what you can do with it. Then I will do a code walkthrough writing a base channel in Tcl. And depending on what, if you have more time, then the other code walkthrough and or the demos of. So history, examples, base channels. First, base channels or channel drivers, basically everything which can be represented in memory either as a block of bytes or as a stream of bytes. That is something we can represent as a channel and then write a channel driver for. And the simplest ones are basically def null, portable def null, portable def zero, random generator for random bytes, or everything which we have in memory already, like strings, variables, and whatnot. Memchan is actually it's basically a variable, but you don't see the variable, it is hidden then in the driver. And FIFOs are in the same manner. It's also based on variables and it's hidden in the driver. And for regular FIFO, it's basically a U-term, and that doesn't help us much. FIFO 2 is basically two channels which talk internally, and at that point you can do in-memory connections between different parts of the Tcl script. Am I not loud enough? Yeah.
They can't hear you back in Germany.
Yeah, let's see if that works. Okay, FIFO 2 basically in-memory communication between different parts of Tcl scripts or across threads, which is most likely the important application of that. Then for transformations, we basically have a few categories, namely simply observing the data which is flowing through the channel, but not changing it. We can take action on it, but we are not changing it. And then transforming, like doing encodings or to impose chunks on the data which were not before, or remove such chunks. Then compression, encryption stuff, things like that. And we also can basically create transformations which limit the input, artificially inject some end-of-file condition based on patterns or the size of the data, things like that. And back to the observing, as I said, we can do actions like gathering statistics or diverting a copy of the data to somewhere else, basically a probe point if we want to inspect the application during debugging, and also in other applications checksum speed, CRC, Adler, whatever. Good. And for writing a base channel, we basically have three things to look at, namely the construction and destruction, creation, tear down, then how to handle reading and writing the data, and also event management, that is basically for everything non-blocking channels which are so beloved by us in whatever. And good. The basics are, this is the basic creation. I'm using Tcl Donald's OO system to create the handler script. This is not a necessity. You can use namespace assembles, commands, procedures, whatever you like to implement the handler for the channel driver, as long as you provide all the necessary methods, which I am basically walking through here. And I have basically I have a class for all the methods, and I have one command to wrap around the creation process. And the main command we are seeing here is chan create. This is the command to create a new channel and associate it with the handler command to implement the driver.
Andreas, if you step back a bit, you're in front of the...
Okay. Better?
Yes. Good.
And in the construction, basically, I am setting up some data structures, which I explain later a bit more. And the first method we get from Tcl, which is called from Tcl, is the initialize. method where we then set up a bit more and also tell Tcl what methods we are supporting, and Tcl will check that we are supporting everything which is needed or that we are basically doing everything right. And mandatory are initialize and finalize. Read and write are optional. Basically, you can have read-only channels or write-only channels. And the configure stuff is also optional. Your channel may have options or it may not have any. And actually, configure and cget have to be configure is needed, or cget and cget all is needed. You can have read-only options or write-only options, so you can choose there a bit more. The watch method is needed for the event handling. If you don't have that, then your channel is not supporting events. And the last method is finalize. That is during construction. At that point, we basically release everything. We have allocated, release other resources which are external possibly, and then destroy the handler object in this case. Or if we destroy the handler object, then we will also close the channel. So there's a bit of trickiness involved. Basically, whatever direction we come from, the other side is torn down as well. And configuring is relatively simple. The configure method is called with option, and the value we have to check is the option okay, is the value okay, and set our internal state. Or in the cget option, we are asked for a single option and return the value if that is an okay option or an error if it's wrong. And cget all is basically when you are doing this all comes from the fconfigure command, and if you say fconfigure on a channel without clearing a specific option, it wants all options, and cget all is a method called in that case, and basically tells us, give us everything you know. And in our U-turn FIFO, we have one option, which is the dash delay, which is something for the event management. Normally, the operating system generates events for us through the select system call and stuff like that. However, given that this is completely in memory, we have to generate the events, and the delay option basically tells us how often events should be generated. And this is basically internals to the option handling. I had the check option method and then the check delay method. And here I'm basically checking the option is dash delay. Okay, that's okay. Otherwise, it's an error. Or I check that the delay is also properly integer value greater than 0. And that is in milliseconds. Reading and writing is relatively simple. We have the methods read and write. For read, we are told how many bytes are requested from the C level, and for the write method, we get the buffer with the bytes. And it is important to know these are bytes. These are not characters. The encoding stuff has already run, but Tcl's I/O system has already done all the encoding stuff, end-of-line transformation, and so on. We are seeing bytes here. And this can be tricky if you, say, create a channel driver which then talks to a text widget to display the stuff. And at that point, you basically have to convert it back based on the encoding set on the channel. In my examples, I actually are not doing that. I'm sort of expecting that you are getting only ANSI characters, and at that point, we don't have to convert back. But that is actually a bug. It is not really the right thing to do. And in this case, with the FIFO, we have one buffer where data is appended to the end and data is read back from the front. So in case of a reading, we basically take that many bytes from the front, reduce the buffer, which is the data variable, by that much, and depending on if we have enough data left, we set up the event management system to stop generating read events, or even if we have nothing read, absolutely nothing, then we return a special error to tell the channel system, I currently have nothing, but there may be something later. So that is basically the again error. Try again later to get more data. If we were returning the empty string, the I/O system says, okay, that is end of the file, done. And that is why we have the special condition. Otherwise, we simply return the data we have taken. In the write case, we are simply appending, and we are setting up the event management system to say, okay, we could now post read events if read events are requested. We are coming later to that as well. And one thing, we have to return how many bytes have been written. That is the usual thing. And all the interesting complex stuff you need in this channel driver is now hidden in the C level of the implementation, and makes it basically this easy for us to write the thing. And this is now, we are starting now with the event system. The data, I haven't commented on that, that is basically our buffer. We have the channel to make the events for, and the timer variable, which is the timer to generate the stuff, the delay stuff, and we have basically 3 types of data. What events are allowed by the channel state, that is what we saw in the read-write, allow or disallow read events, and in the construction, the write events are allowed always. And then we have a set of requested events, that is what is coming through the watch method from a particular I/O system, which tells us I need read events, I need write events, or both, or none. And the posting variable is basically the merging. We are computing, okay, we can generate this, we want that, and that means we have to generate this intersection of both, basically. And we have here the watch method. We are basically looking if it requested something different than before, and if it didn't, then we simply bail out. Otherwise, we update our information and compute the intersection in the internal method. And this is basically the graphic. From the watch method, we get the request information. From the disallow-allow methods, we get what is allowed from the channel state. And in the update method, internally, everything is merged together, and we get the information about what events to post. And then we have the start timer method and the post method, which actually post these events based on the delay information until basically the watch method tells us stop. And here are these internal methods on the allow side. Basically, we have allow disallow, which goes into one central command, which updates the internal states. And if there are no changes, we bail out. Otherwise, if there are changes, we update the set of events to post. This is something which I have written out here in detail. This is also something which is common stuff and can be put into a core class, basically any other channel driver could inherit from. And in the code which comes with the paper and the slides, this is exactly what I have done. Basically all the example channels use this event system from the base class. And last, the intersection is also relatively easy. We stop the timer if it's running, and then we look at the requested events, if they are allowed or not, and add them to the set of posted events. And if we have something to post, we start the timer stuff. Otherwise, we kill the timer variable completely. And the timer stuff, start timer, and posting is the standard stuff. We have to generate a recurring timer. Basically, normally after is a one-off timer, and here we are basically rescheduling the timer after posting to get it done, or basically every 10 milliseconds. What is interesting here is this namespace code list my post. This is the standard way of basically invoking the method in the proper namespace, namely the namespace of our handler object. Okay, that is everything. What is our time now? 50. Yeah, I guess we can do the transformation as well, which has the same 3 things: construction and finalization, and reading and writing. One thing I should possibly go back to, in my simple example, the channel is not seekable, so I didn't provide the methods for seeking. In the code examples with the paper, we have some other channels which do seek, and there you can see how that works. Basically, you obtain a position where you are, and then you move back and forth and take the data at the proper place or insert it at the proper place, plus checks that you are inside the boundaries of a range, basically. Yeah, the transformation is, the basic stuff is the same class with the wrapper command to create things. Here the command is chan push to create the transformation associated with the handler command and associated with an existing channel. And we are in the construction, and we have the same thing, setting up some variables and returning the methods we are supporting for checking. And in this case, we have the regular initialize, finalize, read and write transformation, and the special plain and flush methods for special conditions where we have to basically clear our buffers in various ways because the channel is currently shutting down, is flushing stuff, and things like that. That comes. And in my example, this is a base 64 encoder, which encodes on writing and decodes on reading. This is something which a proper channel could be made more flexible, switch what is done on what connection. And finalize is the same thing as with the FIFO channel, whichever side, whether the handler or the channel is closed, the other thing is destroyed as well. And we are releasing our data. And here we really don't have data to release, but that is one way to do that. This is now the read side. The interesting thing here is we are getting the data to transform. Again, these are bytes, not characters. And here, what I'm doing here is basically I am putting this into the decode buffer. I am decoding groups of 4 bytes and only groups of 4 bytes. And if there are 1 to 3 bytes left, they are left in the buffers and are not decoded. And everything which I have decoded, this is returned. And in some cases, basically, when the channel is seeked or is closing down, we have to force the transformation, even transform the incomplete groups, basically our groups of 1 to 3. And for this, we have the drain method, and we also have a clear method to completely discard any partial stuff which is left. And internally, this looks like this. We are appending to the buffer. We are computing how much complete groups we have. Then we run it through the binary encode decode based 64-bit command, which is also new in 8.6. So I'm using quite a bit of new stuff, which is in 8.6 and not yet in 8.5. It could also be some TRF or Tclip. They all provide base 64 for all versions of Tclip, basically. And yeah, the method to compute the complete groups is basically divide by the number or by the size of a group and multiply it back again so that you have. And that is not really the interesting part, I guess. Writing is basically this, the same way, except that we are now encoding and the groups are of size 3. Basically, 3 bytes become 4 bytes, base 64 encoded, and in the read part we have our 4 base 64 encoded bytes, which become 3 regular data bytes. And here we also have a method to handle partial data, which is now flush, and it basically does the same thing as the drain. Okay. That was the code walkthroughs. I guess we can try some demos if we have time. Yeah. Okay. While he is getting it back up to running, I can ask questions, I guess.
I have a short question. Do you have a generic way to handle incomplete UTF-8 characters?
A generic way? No, not really. This is actually something I looked into when I did the text window base channel driver. It would have been nice if I could do encode and convert from or convert to, and then get back the information. Okay, I converted this many UTF characters and these 2 bytes I couldn't decode. I didn't see a way to do that. That is something which you should look into and see if you can adjust that. Anybody else? Okay.
That's great.
I was looking forward to an example of this. We've got a particular application where we need to start writing our log files zipped and maybe even zipped. And under Unix, that's okay. You just pipe it out to gzip and pipe it back in from gunzip. But on other platforms, like Windows, that's a little difficult.
We have a zip transformation. Well, I wrote a zip transformation as example. However, in TLL6 we have the zlib stream stuff by Donald, which is basically the same at the C level, which provides access to some more data like the gzip header and things like that, which my transformation doesn't.
So this was very good.
This was working now. Basically, what this is, we have a transmitter and a receiver which talk to each other. It is basically a toy secure file transfer application. It does first the toy key exchange stuff and sets up an encrypted channel using a one-time pad. And the one-time pad, the key for that is basically a series of random bytes derived from the exchange key. And that uses the random channel I mentioned in the examples, and it uses the runtime pad transformation to perform the encryption. And to see what is going on, I have at various points observer transformations put into this thing, which diverts the stuff into a different channel, and namely the text window channel. And given that most of the stuff would be text, so we could see it directly. However, I've put, normally we have binary data, and for that I have put some other transformations on top of the text window channel to hexify it, and then to make it into groups of 2, and then also basically chunking at the second chunk to split it into lines. And we basically see here what is generally going on about the connection. Yeah, what is going on about the connection. Then the hexify, this data hexified. This is the random data stream, the random bytes for the encrypting. The clear data and random is encrypted, and then it comes back on the receiver, and it has the same random data and it's the same encrypted data, decrypts it again with SAW, and we see the result. And it is a toy thing, because there are definitely stuff which is more secure or better, say TLS. However, it should demonstrate the stuff. We have lots of channels and transformations for the encryption, for the random bytes, and to observe basically what is happening internally, probe points basically. Yeah. What other example could we show? Yeah. Show the pump maybe. Yeah. It doesn't need to see what. Here, try 16. This doesn't show much. What we did now was the checksum example. The checksum tickle file is applied to itself. It computes various checksums via transformations and simply spits them out. And I have basically my ATLA 32 checksum from Donald's ZLib stuff, and I have implemented this transformation in pure tickle as well. You see both have the same checksum, so I was obviously right. And then a counter, basically it was 635 bytes, and a CRC checksum as well, also from Donald's ZLib stuff. And Jeff, can you open the checksum tickle file?